Okay, we can start again. Nicolas.
Thank you very much. So I'm going to present a talk about something fairly practical, which is the idea of post-processing Rocq proof scripts. So if you have experience with Fiora improvers, you can do a lot of proofs, and then in the end, when everything works, you feel like, okay, maybe I should redo that in a better way, but you're tired, you don't want to, and you want to the next problem. So together with Alexandre Jean, who is a PhD student in Strasbourg, we devised a few tools to try and help people have better and refactored proofs once they have completed the main work. So as you know, proof assistants are increasingly popular, and proofs remain highly technical and difficult to reuse. And sometimes when you want to reuse something, you don't understand how it works in the base case. In the worst case, it doesn't work anymore for some reasons because you use some inversion tactic and it decided that it requires one extra argument or something like that. So here is a small sentence which summarizes usually what happens is that once the proof effort is done, the proof scripts are left as they are, and they often break when upgrading to some recent version of the prover. That's something people usually hide under the carpet. So they tell you, okay, it's very easy. Yes, we'll reuse some development from 20 years ago, but they go very quickly on the part. It took us half of the time to make it working again, and then we improved it. So the idea is to set up some infrastructure to be able to do some what I call preventive maintenance. I mean, instead of trying and fix it when it's broken. If I can take an analogy, for instance, when you drive your car, you don't wait until it's broken to get it fixed. You get it fixed periodically just to make sure when you're on the highway, it doesn't break and it works properly. It's kind of the same idea. So there are several transformations that we think would be interesting and that we studied. So the first one is about adding structure to proof scripts. So in the Rocq proof language, using brackets, using bullets, and this kind of stuff. Another one is replacing calls to auto or LTAC tactics with the actual proofs they do. And remembering, okay, it's been generated by auto, so in case it doesn't work anymore at some point, okay, I will redo auto and fix it. Again, making all variable names implicit or explicit, I'll come back to that later on. And maybe sometimes you want to inline some auxiliary lemmas. For instance, when you're doing formal proofs and you don't want to use the mathematical components library, but you require a lemma which is 2 lines of mathematical components. Maybe you want to inline the lemma so you don't have to import half of the library. Just to do, yes, that's a weird idea, I know. This happens. And if you add structure to proofs, I will show you in a moment that you can make very concise proofs. But if you do them, if you make them very concise, then you have a problem because one is broken. If you want to debug, it's just fails. And you don't have any proof steps available. So you want to sometimes expand your proof script so that you have every proof step, which is an atomic step. Okay, so for those who are unfamiliar with Rocq tactic language, you have basic tactics. So intros, apply, elim, induction, split, lia, nia, whatever. You have tacticals, which has the semicolon, the square bracket, the pipe. And you have some subtle stuff. If you do solve or first, it doesn't do exactly the same, but I don't know exactly how different it is. You have more advanced tactics like auto intuition, which will do some stuff you know about if you're a Rocq developer, but you don't really know about if you're not if you're a beginner, for instance. And so the first example I will take is just because it's funny, because I'm not sure it's very, very useful in real life. but it's to transform a proof script into an equivalent single-step proof script, which means you have a proof script with like 10 lines of proofs, and you want to do it in one line using the semicolon, the brackets, and the string. So the example is a simple one. It's distributivity of or over n. It looks like that. So if you have a lemma for all A, B, C in prop, and you have A or B and C implies A or B and A or C, then you can do the proof the way you would do it if you're a regular Rocq user, and you're if you're a very good user, you might be able to write that correctly in the first go, but it's quite difficult not to forget something. And if you get an error message when it's broken, it's not very readable. So you do some introduction. Destruct will say, okay, from A or B and C, you will have one side when you try to prove the conclusion with the assumption A, and on the other part, on the other goal, you have to assume B and C, and you have to prove A or B and A or C, and so on. So you can do a proof. So we want to have a tool that can transform this statement here into this one here, which is a one-line proof, which means it's executed just in one go. There's not much interaction with kernel of code. There's just one tactic which is elaborated into a term, and then it's over. Whereas here you have some interactive steps, and at each step you check that everything is okay. So this is very nice, but it's nice for library, especially it's nice when you want to compile them, because as we'll see later, it's a bit more efficient, but of course it's very painful for debugging. So of course we want to implement the inverse tactic somehow, which means fully expanding and structuring the proof scripts. So this looks like that. You have the proof on the left, and you get back to the somehow initial one on the right, but here you have a bit more structure, but you have the bullets, which helps you know that at some point when you do destruct H, then you have two different goals, which are the one with the plus bullet, and then you have some subparts. Okay, so you can run it separately, and at some point you can figure out where you stand in the proof tree structure of your development. Okay, so of course this one is it's much more usable, the one on the right. And so we made some experiment to see how, what kind of transformation we can get if we do some compact proof. And from when we looked at the library, the Arith library of Rocq, or the high school geometry library of GeoRock, because I replaced Coq with Rocq everywhere, and I forgot that GeoCoq is still called GeoCoq at the moment. Somewhere else in the slides, I have GeoCoq, but this one I didn't see. Sorry. So when you do the transformation, you have some improvements, which are not very significant. It's about 5%, but when you talk with Pierre Boutry, you know the guy this morning talking about GeoCoq, when he's recompiling his proof development because he might want to change the axioms. So the axioms, usually they are in the first files of your development. And if you want to recompile everything, it can take a while. And he says, okay, usually it takes 15 minutes to recompile. And if it only takes 14 instead of 15, I am already happy. So that's an example where you see that this could be useful to have this kind of transformation. So now I will switch to a more generic framework when I will explain how we can do this kind of transformation together and how we can mix them together. Okay, so we developed a tool which is called Rocq Ditto, but in English, I think you say it in another way, but the I being Ditto or something like that. I don't know. Anyway. So this is an external tool to perform source transformation of Rocq proof scripts. So it's written in OCaml as a library which handles Rocq abstract syntax trees. It's based on Rocq LSP, which is developed by Emilio. And what does it allow? It allows to do some abstract syntax tree transformations. And it also allows you to have pretty printing facilities so that your proof development, once it's been transformed, it still looks like a proof development with new lines when you have a point or things like that when you have the end of the tactic. Because if you do a transformation, for instance, if you look at your proof development and you figure that you have 3 steps in your proof and the third one is useless, if you basically remove it from your script, but you do not reshape your script, it's a bit annoying for the reader, which is like, okay, there's big holes in the proofs and stuff like that. So you have to do some layout. You have to take into account some layout problems. So that's why we have a dual representation of proof, which is as a proof tree and as well as a linear structure, which is exactly the structure of the proof tree. It also allows for speculative execution, which is useful when you're trying to reconstruct what happened when you did some auto proofs or this kind of stuff. So it looks like that. It's nothing very fancy. So the internal representation is here you have a Rocq proof script, which is linear, as I said, and then you have a proof tree, which corresponds to this sequence of tactics. So how do we define a transformation with our tool? So a transformation is a function that takes as a proof as our input and returns a list of transformation, which are one or more of the following ones, which is to remove something, to replace something by something else, to add something more, and to attach is something that's going to tell you how it will be pretty printed in the scripts. This is where you will link it in your proof structure. So I will present 4 different case studies, which are meant to exemplify what we can do with our systems. So this is not closed at all. It's just like suggestion, and I'm very open to hear some new suggestions. We started with very basic stuff, and then we extended it with Pierre made a teaser this morning about this story about constructivization of the Geocoq library, where he said that when you want to make the library more constructive and it wants to implement some automated transformation, so that's kind of stuff we managed to do. Okay, so here are I think I told you already what's written here. So it's about structuring, compacting the proof script. So I already introduced it in the introductory example. There is the issue of replacing autocalls by their actual proof steps. The issue of explicit naming of automatically introduced variables. So here we choose to make the name explicit. Maybe we may want to have the other way around, meaning that maybe you want to have implicit naming for everything and no names at all. But if you want to have no name at all, if I give you an example, if you do intros H and then you do apply H, if you want to have it with no names, you have to do something like intro, assumption, or something like that. And if you do assumption, it's not as efficient as doing apply H. And this is a very simplified example. It's probably even more complicated than that. So putting explicit names makes it easier to implement, but maybe it's not the best approach. And the fourth possibility is to work on some global proof transformation, which is, for instance, the constructivization of the Geocoq library. Here I wrote Geocoq and not Georoq. So here is another example. So you see my examples, they are very basic and logic-based. So it's something that said like if P implies Q and Q implies R and R implies S, and I have P or S, and then I can deduce that I have Q or R or S. Okay, so this is kind of stuff you might encounter with some instantiation of P, Q, R, and S. And so the proof can be achieved in the way that's presented on the left-hand side. Maybe you can do it differently. Maybe you can even do it directly with auto. I'm not sure. For sure, you can do it with Toto. Anyway, and so you have this auto thing here, and you want, so here the example is very basic. So, okay, that's not very significant to replace it by what it actually does. But in more complex example, it could be useful. So you want to replace the call to the auto tactic to what the tactic actually did. So what the tactic actually did, it did some simple apply with some basic constructors and with some of the assumptions which have been explicitly named on the line before. So the idea is how Rocq could help us find what auto did and how can we replace this auto tactic with this succession of simple tactics. So for that, we use something which is a tactic which is called info auto, which provides insight about what auto does, but it doesn't return what has been achieved by auto. It's somehow summarize what have been tried by auto. So it's the list of everything it tries with no explicit explanation of when some backtrack happened or we didn't manage to use it properly. So info auto provides, instead of says when you call auto, it does something like that. So you have to build a tree from this information. So the indentation provides you insight about how it's organized. So it's organized in that way. And not all of the tactics that appear here are relevant. Okay, I have no, yes, because it's involved. So the only relevant ones are these ones. And so it's or RL. So it's going on the right-hand side, okay? It's simple, apply on or, and going on the right-hand side. So you have to select all the tactics that you need to apply and remove the useless one from the output of info auto. So that's why you need some speculative execution of what happened, what's been proposed by the info auto tactic. Next example is how do you proceed to name explicitly all of the variables? So basically intros is something you can do with no argument, but there are many other tactics including inversion, induction, destruct, and a lot of and some other ones which allows to be written, which will generate new names which has not been specified by the user. So for instance, if you have something like intros, we write IHA, you want to transform it into something more relevant, which is intros. And so I didn't write the actual statement, but NM, HNM, and IHA, and then we write IHA. So when you have the explicit name, something that's a bit counterintuitive is that if you change something, your script will fail earlier, which means, for instance, you can imagine that IHA is something that's the result of the induction because the variable was used, and because if it's IHA, it means that your inductive type is something whose name starts with A. And it happens, for instance, if you want to do a lecture in French and you start, okay, inductive nat 0 successor, and 5 minutes later, you realize that your students are French and don't understand when you write stuff, you want to call it entier instead of nat. And if you call it entier instead of nat, then everything that's generated automatically, which used to be N something, is E something. And everything is broken for, so of course my example is a bit silly, but with some example when you're trying to fix what you want to use as data type and what we want to do in inductions, it could be very useful. So the way it's achieved is very simple, is that you apply your tactic with no arguments and you retrieve from the code context what were the name that the system chose to give to the object, which has the interest of being safe, because as you know that you're post-processing a script that works, you know that if you explicitly write the names that have been implicitly given by the system, of course it will work. You don't have to guess anything, it's already known by the system. That's what's written here, I think. And so now all names are automatically and explicitly specified. And last but not the least, you have this idea of doing some general transformation to a library. So the example is the constructivization of the Rocq library. So Rocq library, you know it from this morning. In case you don't remember everything, it's a formal Rocq library. It's one of the largest in, maybe MatComp is bigger, but it's quite large library, which formalizes geometry up to its arithmetization. It's based on Tarski axiom for geometry. And in addition to the usual axioms of Tarski for geometry, you have an extra assumption, which is the decidability of point equality. And doing the constructivization means that instead of assuming some decidability property, we want to remove them and use something weaker. So it's based on a result by Bison, which is in the paper a constructive version of Tarski's geometry, where he says, okay, we can remove the decidability of equality, and we can deal with we can do the constructive description of Tarski's geometry, but he's only doing it with a pen and paper. And so that's worth trying to check on a computer that is actually right. So here's a nice picture trying to explain what's going on. So you have the excluded middle, which is something very strong. Then you have something which is decidability in a type, which is something a bit less strong. And then you have decidability in prop, which is what assumed in Rocq. This is what the point equality says. And then you have the concept of stability, which is something that's strictly weaker than decidability. So if you have a new unary predicate P, assuming the stability of P is assuming that for X, the double negation of P of X implies P of X. So it is trivial to check that if a unary predicate P is decidable, then it is also stable. And so you have issues about how to deal with the usual connective. So here for and it's easy. If you have A and B two propositions, if you have stable of A and stable of B, then you have stable of A and B. In the case of the disjunction, it's a bit more complicated because such a statement with or instead of the end at the end of the first line does not work. So you have to define a new predicate, which is not A and not B, which is noted with this square or notation. I don't know what's the name of this symbol, and which preserves the stability of proposition. And then you can, from this first property and taking the stability of point equality instead of the decidability, meaning that you assume that if you have not X equal Y, then you have X equal Y. Then you can deduce the stability of some predicates of the Rocq library, which is especially the predicate Kong. Predicate Kong is the congruence predicate, which allows to say stuff about equality of length of segments, for instance. But you cannot say do the same thing with the betweenness predicate. The betweenness predicate is to say that a point is on the same line as two other points, but in the middle of the two, in between the 2 points, not necessarily in the middle. So to be able to apply the betweenness, you have to assume that you have at least 2 different points. So you have for all A, B, C, A is different from B, implies not betweenness of ABC, implies betweenness of ABC. So you see that it's already very intricate to change stuff. It's not just you take the decidability predicate and you put something else instead. You have some machinery to put around, and it's a bit technical. So what we do is that we use our prototype to do some useful transformation for this purpose. So because we are trying to do constructivization, of course, we need to remove all proofs which involve exist in their statement, because at the moment we don't use them directly. Then we need one that replace usual predicates with their stable ones. So for and it's easy, because for and you have stability, so you can keep and. For the disjunction, you have to take an alternate predicate which doesn't have exactly the same properties. And then you need to replace the classical tactics you will use usually, like left. And you have to replace by something which is called the stab left, which will take in charge the new stable or predicate to be able to do the transformation. So far, we managed to translate a few chapters of Starsky description of geometry, and our tool proves a nice helper to do the translation of this library into a constructive one, and it's still work in progress. We are going through all the chapters and fixing the tool because we have to identify what are the actual needs during this large transformation. So now we've seen some several examples. The next question, which is the main subject of the PhD work of Alexandre Jean, is to determine how this kind of simple transformation can be combined so that we have some powerful tools. The idea being that sometimes we have some notion of optimum solution, which means if you have a proof script, you might want to transform it, but depending on whether you like proof to be readable, or whether you like proof to compile fast, or whether you like proof with no assumption tactic, you might have different needs. So which means you have no normalization process, which will transform a proof into the best practice proof, because the best practice proof is some kind of multi-criteria evaluation. So that's the issue, is what an improved proof script. I think if I ask the question in the room, no one agrees on what would be a nice proof script. Somehow, we would like, in a perfect world, we would like that when you do a proof and you want, when someone does a proof and you want to reuse it, you would be able to say, okay, the way I want it to look is my criteria, and you can transform it into your way of doing the proof. And then if someone wants to reuse what you've produced next, and if it's the first person, you can reverse it to the initial way it was carried out. So it highly depends on the user. So the 3 basic examples I thought about, but maybe there are other criteria, is the compilation efficient issue, the readability issue. A lot of people are concerned with how proofs are readable, and that's one of the criteria to trust a proof system. It means that if you have, if you do some interactive proof and you do a proof in Rocq, and no one can read what's been achieved, there's not much difference than using a SAT solver to do the proof. It will answer SAT, and you won't get more information. But what you did, you're writing 500 lines of proof, for instance. So readability is an interesting issue. And maybe you want to have shorter proofs because it takes a lot of space in memory, or for many other reasons. So the issues that needs to be addressed is one of the first issue is the issue of reversibility, which means if you do a transformation, can you do the opposite one, and do you have a idempotent transformation? So it's almost the case for when you structure and unstructure the proof, which means you will reach a fixed point at some point because you will have the transformation from bullet proofs into square bracket proofs and back and forth. You have the issue of compositionability, meaning can we combine some transformation? Of course, if you take a transformation about the structure and you take a transformation about the names of the explicit namings of the variable, it will be fairly easy. But for other transformation, it might be a bit more complicated. You have the issue of the appropriate order of the transformation. And then the most difficult one is this issue about optimality, which is a largely open question, is what's an optimal proof? And maybe we can do a poll at the end of the talk to see what's an optimal proof for you. Okay, I'm coming to the end of this presentation, so I will summarize quickly what we achieved and what we want to do in the future. So we have a framework which operates and actually allows us to refactorize the proof script in very different ways, and accounts for multi-criteria optimization. So it allows to accommodate various proof styles. And we managed to implement some specific transformation to achieve the constructivization of the Rocq library. And in the future, there are some very simple direction and more complex ones. So the first one would be to find a way to remove all occurrences of named variables instead of having some explicit naming, which clutters even more the proof script. The idea is to do some benchmark on what we can achieve on a larger library. So for instance, the whole of the Rocq library or the STD++, or maybe we can try and see what happened with Concert, for instance. So see what happens when we scale, because so far we only handle files one by one, and maybe we want to be able to deal with a larger library directly. Another issue which is a bit more theoretical is thinking about more abstract data structure to represent the proof script, because so far we have a very basic representation, just a tree-like representation of what happens in a proof script. And something which is more long-term and will require some more intense cooperation with other people in the field is how to integrate this kind of stuff to VS Code. So for instance, if you extend a proof, maybe you have two styles, one style that's the main style and the other one that's the concise style or whatever. So that could be a nice idea. It's fully available on GitHub, and I listed here the recent publication. So there will be a talk by Alexandre Jean at the Rocq shop at the end of the month, and this work was also presented in other conferences. And I thank you for your attention, and if you have any questions, I'll be happy to answer.
So when I heard of a proof script transformation library, I was also thinking of automatically golfing your proof, such as if you have two subsequent intros line, combine them, or perhaps if there's one low-level tactic replaced by a higher level tactic, or somehow write the same proof in a shorter way, in the same way that you perhaps teach a beginning Rocq user. Like their code, like the 7 lines of code can in fact be 2 lines of code that's equally readable. Are these directions that you have thought about?
Yes, we made an experiment where we took a proof script and we execute first line, and then we check if something changed, and we execute the second line, and so on. And then in the end, we figure out, we remove the useless lines from the script. So it can contribute to less readability, because an example is if you do a proof step by step, if you have some computations in your proof, and if you have something like simple at some point, and if you remove the simple, then when you're reading the proof, you don't know that you write, let's imagine you write simple dot and then assumption dot. If you remove the simple, then what will be displayed on the screen is not obviously solved by assumption, because it might require some computation, but the kernel will do the computations. But for the user, will be a bit more difficult. But one idea is to, yes, try and make the proof, like one point of view could be to make the proof shorter. As I said, it makes them less readable from this point of view, but more efficiently compiled and so on. There are a lot of perspectives indeed.
I was more thinking of some, let's say, reviewing lots of pull requests by new contributors in Mathlib. I somehow have the feeling there's certain patterns that are almost obviously not optimal, that you almost always want to compress. So I wonder if there's a way to somehow capture these more intuitively. And it's not a question just of readability, but more like, yes, we obviously want this.
I will investigate that. I don't know. It's a good idea. Thank you.
So at the very end, you said this is not yet integrated with the editor, so with VS Code or things like that. So how does it work? You have a script on that you launch on the command line?
Yes, you have a command line function, and you will take one .v file and put this another .v file. Then you can compare them. I do not have the technical skills to do the integration in VS Code, but if someone wants to help, I will be happy to use it.
We had this one example where turning a proof script into a one-step proof script made everything 5% faster, right?
Somehow, yeah.
Do you have any idea why this is faster? Intuitively, it should be the identity in terms of performance.
My understanding is that you have a handling of the context at each step of the proof, which if you do it as a one-liner, you just have the initial context and the final one. And so you don't have any intermediate step where you have the Rocq engine trying to make sure what the state is okay and so on. That's my understanding, but I am not a specialist of the internal of Rocq to be sure.
Maybe it's a blurry question, but I feel one thing that's quite important is somehow the intent of the writer, in a sense that that's something that's kind of get lost when you have these sort of automatic translations that like as you said, you do it once and you go back, but then the thing that you go back has been somehow normalized, and often you've lost some things in the original text that maybe like new users were kind of just doing it at random, but advanced user maybe had a reason to do it. So I guess my question is like, do you have any idea how this sort of intent can be preserved in some sense with these sort of transformations, or like how like maybe the original writer of the proof could maybe have, I don't know, signal to the tool somehow like, oh, this part I don't want you to refactor because they have some reason for that. Like
while you were asking your question, that what I was thinking is that maybe we can add something in the tool that says don't touch this part. But it's too early in our experiments to know whether something is lost or not, because it would be a quite a long experimental setting, because we need to have a development, do the transformation as the developer, if he recognizes if he feels that this development is his own, or if it isn't. So it's a bit more difficult, but yeah, we can have some highlights that say, oh, you don't change that.
Maybe the other way around. I mean, if you end up having some sort of integration in the IDE, maybe that's something that like users can choose to like use or not, and it's the other way around.
Yes, that can.
By default, it's
then
not
in
changed,
this
but if
case,
they want, they click the
so
button.
far, it's not interactive. It's interactive in the sense that you have a list of transformations and you can combine them, but you do not decide. You don't have your script and say, okay, I change that, and you see how it looks like. And far, it's not developed in that.
So I don't. Maybe I didn't understand it. If you said it, but the transformations you apply to the for the constructivization of the Rocq library, is it something that you made so that it can be easily adapted to other transformations that you would like to apply to other libraries, or is it specifically
So far, it's not. So far, it's a bunch of several transformations we are listed here. And we combine this transformation, but we're just trying, and like this is our case number 0, I would say. So we're trying to see what we could do. And when we fix a problem, we try and fix it. So it's try and errors at the moment. So once we have something that works properly for this transformation, we might consider how we can generalize it or reuse it in another setting.
Question myself. So far, your transformations work on scripts that work.
Yes.
It would be very nice to have this kind of intervention when the script is broken.
Of course.
Do you think you can?
There are some work on proof repair which have been done by several people in the US, most of them. That was one of my initial statement, is that I wanted to have some, so I didn't say the word, but I think I used it in previous talk as like the idea of having a linter, like something that's gonna make your code better, the code being proof theory, like Rocq proof script in that case. But my idea was really that for me, I don't know, maybe some people here, they feel like doing proofs in Rocq is very easy and relaxing, but I find it very interesting. I find it funny in some way. I like entertaining to do proofs, but when it works in the end, I feel like, okay, I have no more energy to try and make it better, look better. And so that's more focused on this part, making it look better, be more easily reusable and stuff like that. But I am interested in, but that does not exclude the proof repair issues, because in the constructivization, for instance, that's what happened is at some point you do some proof transformation and then everything is broken. So it would be easy, and Alexandre is working on some small transformation, like small fixes for very basic and stupid errors that appear in the scripts.
Okay, that's fine.